Hospital operating rooms are notoriously plagued with environmental control problems, revolving around the inability to maintain temperature and relative humidity conditions that comply with various healthcare codes and standards while satisfying the comfort demands of surgeons and staff. This presentation provides an understanding of the underlying causes for some of the most predominant of these issues, while giving guidance on how to best cope with them.
Well, good morning. Not yet, not quite afternoon. My name is Dave Schurk. I am National Sales Manager for a company called Innovative Air Technologies out of Covington, Georgia. We are manufacturers of desiccant dehumidification solutions for hospitals and other environments. But I want you to understand, I'm not necessarily here today to sell you anything, okay? Although by my title, you'd think I should, and that is my job, and I would certainly appreciate it, if it ends up being that way. But what I'm really here to do today is to identify a problem that we have in hospitals, particularly hospital operating rooms, with regards to high humidity. And these are problems that are omnipresent and ever occurring, right? And what I want to do is help identify what the problem is and then let you know why we're not solving it doing things the way we've been doing them up to this point, okay? And if that motivates you to want to change and do something different, right? You can get a hold of my manufacturer's rep partner, EEI, and me, and we'll come have a more in-depth conversation with you then. But the beautiful thing is today we have all the stakeholders in the room that are important to this conversation. I know huddled over in this corner we have infection control, right? They're a tight-knit group. They're over here staying away from the contractors and the engineers. I understand that. I would do the same thing, but I can't, and I love you guys, don't get me wrong. But what I really like is they're sitting right up front. That's a big deal. I love that, right? But also in the room, of course, we have facilities management people for hospitals, I assume. Show of hands, facility managers? One, oh man, are we going to have a good conversation. How about engineers that cater to them, to design systems, hospital systems? Just one? Two? They're afraid to hold up their hands now, right? Don't be proud. Contractors that service hospital facilities, right? I know we've got more than that. That's okay. You're busy eating. You don't have to show your hands. What I hope to do is bring to you my experiences over the past 43 years having worked for major HVAC-D manufacturers. I add the D to the acronym because I believe D for dehumidification is not recognized as importantly as it should be in that acronym. So I talk HVAC-D with the D being for dehumidification. But what I hope to do is bring my experiences, 43 years serving hospital facilities clients. I spent 15 years down in the Texas Medical Center in Houston, Texas, fixing hospital operating rooms that were having issues with high humidity. And I'm going to tell you right now, it can be done. So let's launch into this. Have a little fun maybe. Learning objectives today simply assess the environmental needs of hospital operating rooms. Okay, what do they need? Discuss some simple rules of psychrometrics. Oh boy, here we go. Who in the room is not familiar with psychrometrics at all? We've got a few. That's okay. Don't be afraid. I'm going to keep this real simple, real high-level stuff, right? Who in the room uses psychrometrics on a somewhat regular basis and is a little bit more familiar with them? Great. We'll have a good conversation as well. I'm not going to get deep in the weeds, I promise that. If nothing else, you now know how to spell it. There is an R between the H and the O. It's not psychometrics. That is a discipline. We are psychrometrics, and if you are on Outlook typing an email, it will not correct. It will always be psychometrics. You've got to add the R, okay? Just so you know. We're also going to understand the importance of the air's dew point temperature. Who's heard of dew point temperature before? What? Infection control. Wow. Impressive. Impressive. All right. Anybody else? Engineers, contractors. Dew point temperature. If you walk away from this conversation today with nothing more than a very basic understanding of psychrometrics and how to spell it, and dew point temperature, I will have achieved my purpose because this is so important to the conversation of humidity control in operating room environments, okay? And then we're going to assess the environmental realities in hospitals. I'm going to tell you what you've got, all right? And if we want to do better, I'm going to make a suggestion or two to get you there. So, hospital operating rooms. Let's look at some numbers, some statistics, if you will, and I've rounded these up, okay, for today. 80% of hospital operating rooms are environmentally unsatisfactory 50% of the time. And most of those are high humidity related, okay? Most lack proper dehumidification. Look at those numbers. 80% of hospital operating rooms, 50% of the time are unsatisfactory for various reasons. We're going to talk about those reasons. You know, I'm preaching to the choir. You know what the problems are, but we'll identify them in a little more depth moving forward. So why the problem? Huh? Why the problem? Right there, right? On your left-hand side, it's the surgeons. They're the problem. They're always the problem. You know, if it wasn't for humans, this whole world we have wouldn't be a big deal. We wouldn't have a whole lot of problems. The surgeons are the problems, right? They want their operating rooms cool. Gosh, how dare they? In fact, they want them cold. Cold. I say cool. I'm being kind there. They want them cold, right? And the problem with cold operating rooms is with regards to humidity control, all right? And I'm going to talk about that and why. But I'm going to tell you right now, if they want it cold, they need it cold. They deserve it cold, and we need to make it cold. Why? Because they are profit centers for hospitals, right? And profit's not a four-letter word. Profit's important to hospitals. My wife just had a hip surgery on Monday. I was allowed to see what the insurance bill is going to be to the hospital for that one single hip replacement operation. It was $65,000. Her surgeon does 6 of them a day. He has 2 ORs dedicated. He flips back and forth between the 2 ORs. As he's doing surgery in one, they're scrubbing the other one, getting it ready for his next surgery 6 times a day at $65,000 a pop. Wow. They may be prima donnas, they may be hard to please, but we certainly need to cater to them because they are what brings the money in that keeps hospitals churning and burning and chugging, right? Important people. One of my facility manager's friends down in the Texas Medical Center gave me a quote, and I wrote this down the minute he said it, and I've used it for the last 25 years. He said, "Proper environmental control ensures our hospital will maintain the surgical procedures that yield the most profit without fearing the loss of surgeons to competing facilities where OR conditions are more comfortable, more satisfactory. They feel more productive." All right? They can go anywhere they want. And as a hospital, do we want somebody that's doing a $65,000 surgery 6 times a day to go down the street and practice somewhere else? I don't think so. All right? So we're going to talk about keeping them happy. Now, let's take a look at a typical ortho surgeon, right? You see anything here that might raise a red flag when it comes to the ability of us to be able to provide comfort for these people? I mean, look at them, right? Surgeon on the right, 2 or 3 layers of outer garment, gloves on, the space helmet, right? Operating under high intensity levels of lighting, moving around. And I don't want to get too graphic here, but I'm amongst a bunch of medical professionals. They're cutting you apart. They're rolling you around. They're putting new joints in, gluing them together, rolling you back around, sewing you up, right? And guess what happens underneath all that gowning real quick? All that level of activity. They begin to, someone said sweat. Surgeons don't sweat, they perspire. All right? They glisten profusely. They get hot. They start to sweat. It gets wet underneath all that gowning. They become unfocused. They become miserable, right? And they say, "I'm hot. I want it colder." Right? But what they don't understand is what they really want is for the environment to be drier. Yes, cold is important. They do want it cold. In fact, they usually want it somewhere around 60 degrees Fahrenheit. But they also need it dry, and here's why. We need to encapsulate them in an environment of air that is dry enough to be able to wick the moisture from their skin through 2 or 3 layers of clothing into the air that surrounds them, to evaporate that moisture from their skin and to evaporatively cool their bodies. 25% of the way that we as human beings maintain our physiological comfort, if you will, from a temperature perspective, is through the evaporation of moisture from our skin into the air that surrounds us. Look around the room. Look at all the exposed skin. And although it isn't a ton, it's certainly more than these surgeons who are hermetically sealed in cellophane, right? There's no exposed skin. There's no chance of evaporating moisture from their skin into the air. And for every 1 pound of sweat that evaporates from the surface of our skin, we remove 1,000 BTUs of heat from our body. It's not just temperature, it's evaporation. And if we can't evaporate the sweat from the surface of our skin into the air that surrounds us, we cannot maintain comfort, we will be uncomfortable, we will be hot, and we may actually enter levels of heat stress, and this happens to surgeons all the time. So when they say they want it cold, they just want to be comfortable. And it most certainly is a part of keeping them productive, right, and focused. So this is very important. Now, I suggest, and I have suggested for the last 20 or 30 years, and I've documented this in an ASHRAE Journal magazine article that I wrote in 2019, that what I call the point of diminishing complaint falls at the intersection of 60 degrees Fahrenheit and 40% relative humidity. Where did Dr. Taylor say we need to be concerned with the potential for more infection risks below a certain humidity set point, right? 40%. It's a fair place for us to start. But it's also the humidity that's required to assist in that evaporative cooling that's needed to maintain that thermal comfort for doctors. And I call it the point of diminishing complaint. And I'm not suggesting that you have to design operating rooms to maintain 60 degrees Fahrenheit, 40% relative humidity all the time. But if you design them to do it and you need it, you have it, right? And I'm going to tell you right now, and we're going to talk more about this, the orthos want it and they need it, okay? Now there's another issue when we make a space cold but not dry enough. And I don't know if you can see that lower left-hand picture, if you will. It's not very easy to see, but what you're seeing is condensation occurring on a cold, non-porous surface. A register, a grill, above us in the space, right? And when those issues occur due to cold temperatures and excess humidity, and condensation begins to form, take a look at the picture on the right. This is what happens. We start coalescing moisture on surfaces, on booms, on lighting, on registers, on grills, etc., right? And as it gets bigger and bigger, sooner or later, this little thing called gravity takes over and that drop of water drips into the operating environment. Infection control, what happens then? Boom, the train comes off the tracks, right? Boy, is the doc mad. But what's the problem with regards to hospital-acquired infections and surgical site infections when you have liquid water in the proximity of a patient that may be immunocompromised and or exposed to the environment? There's the potential for microbial contamination, mold growth, fungus, bacteria, etc., right? So at that point, you're done. You're done. My understanding is until the humidity excursion passes, you offset surgeries until that condition is overcome. You come in, sanitize, sterilize the ORs, and maybe you're back in business then, right? But a typical OR ortho surgery suite can easily garner $20 million a year or more of revenue for that hospital. And if you're shut down for just a couple of hours and you've got multiple hospital operating rooms, think of how devastating that is from a profit perspective. Not only you have upset patients and you have upset doctors. So we have to eliminate these issues with high humidity, and we can. But these occur all the time. Who's ever had it rain in their OR? Come on, don't be shy, it's all right. Yeah, we got one over here. I'm going to tell you, it happens all the time. Certain times of the year, I've got heads shaking up. Here we go, people are fessing up, right? It happens. It rains in the OR. It's a catastrophic disaster. The train has come off the tracks. We can eliminate that as well and keep surgeons comfortable. Let's talk about how. So I do have to talk a little bit about psychrometrics. I apologize for that. It's not the most interesting conversation in the world, but I'll try to keep it engaging at the very least, at the very most. For those in the room that have a little bit of psychrometric background, who knows what the first rule of psychrometrics is? Anybody? First rule of psychrometrics. It's also the first rule of thermodynamics. Never talk about psychrometrics. All right? But I have to. I have to, okay? I have to. But I promise, it won't be long, okay? I'll make it as short as I can. Psychrometrics is simply the study of the thermodynamic properties of air and its moisture content. And it's used by HVAC engineers and aeronautical engineers and weathermen and all weather people, meteorologists, all kinds of things. Anybody that wants to study the air and what's going on in the air from a standpoint of the air and water combination uses psychrometrics. And this is a psychrometric chart over here on the right-hand side. It's a chart that Willis Carrier put together that looks at all the constituents in the air based on 1 pound of air. Okay, and we're going to look at certain things in psychrometrics such as the dry bulb and wet bulb temperature. Now the dry bulb temperature we use a lot, right? That's the temperature that you would see on a thermostat when you walk over to the wall, and if it's digital, it will tell you it's 72 degrees Fahrenheit in this room. That's the dry bulb temperature. That scale is located along the bottom of the chart from left to right, starting at 20 degrees Fahrenheit on this particular chart and working its way up in 5-degree increments to 120 on the far right-hand side. There are charts that do lower and higher temperatures, okay? Easy peasy so far. Then, everybody's probably heard of relative humidity. All right? Whenever we talk about a space, it's typically temperature and relative humidity related. Those are the sweeping lines that start in the lower left-hand corner and work in 10-degree relative humidity, 10% relative humidity increments from the bottom, which is completely dry air, to the top, which is saturated air, or where condensation will begin to form. Easy stuff so far, right? Then we may look at things like the BTUs of heat in the air, right? We may look at things like the pounds per cubic feet or the cubic feet per pound of air. Those are on the chart as well. And those are important when it comes to making calculations on HVAC systems, sizing air conditioners, sizing furnaces, sizing dehumidifiers, determining the BTUs required, determining the airflow required, et cetera, et cetera. We're not going through any of that today, but we certainly are going to talk about moisture content because that's very important. When I want to dehumidify the air and maintain a set humidity, a comfortable, productive humidity, I need to determine how much moisture is in the air and how much I need to remove. And that falls over here on the right-hand side of the chart, and we got all kinds of stuff going over there. That's where I play every single day, and I love it. That's a great place to be. And I can look at moisture content in the pounds of moisture per pound of air, in the grains of moisture per pound of air, in the vapor pressure in the air. Believe it or not, moisture moves based on vapor pressure differential. The moisture in the air is at a high vapor pressure, and it will move from high to low. All right? That's one way to analyze it. And dew point, our dew point temperature. I mentioned that already and how important it is to our conversation. Dew point temperature isn't necessarily a metric I use in running calculations. But when it comes to analyzing a space, right, from a standpoint of where I want to maintain its humidity level, dew point is incredibly intuitive because it will tell me at what temperature a surface in the space will condense moisture. Think about that. Think about how powerful that can be when we walk into a space and something's dripping. Or when I'm sizing an air conditioner and I have a certain temperature on the coil and I need the coil to be colder. All that can intuitively come to us immediately if we know the dew point temperature of the air that we're dealing with, and that's what we're going to talk a lot about today. Okay? So why do we have temperature and high humidity issues in hospital operating rooms either consistently or at specific times of the year? All right? Psychrometrically, I'm going to quickly talk about that. I am going to give you the chance, if you're interested in quickly scanning this QR code with your phone, it will give you a link to an app that you see here in the middle. And if you'd like to follow the couple of short examples that I'm going to give on the psychrometric chart, you can do it right there instantly on your phone or on your laptop if you download it to that. Okay? Let's keep going. And I'll give you that chance again. Now let's look at hospital operating room design standards and where we are designing hospital operating rooms at today from an environmental perspective. We talked a little bit about it earlier with Dr. Taylor's conversation. This is what they were referring to. This is ASHRAE, Standard 170. This is the 2017 version. I think I'm a little bit behind, but it hasn't changed that much that it makes much of a difference. And ASHRAE is kind of the governing body of heating, ventilating, air conditioning, and dehumidification people, right? It's a nonprofit organization that helps our industry drive standards for various applications. Hospitals being one, being very important. And ASHRAE Standard 170 for hospital operating rooms tells us lots of things. What's the pressure relationship in the space need to be to the spaces surrounding? It needs to be positive. We need to provide enough air to the space that air will exfiltrate out through doors and openings and cracks and crevices to keep the space positively pressurized so that bad stuff doesn't get in and clean air gets out, right? That makes sense. From a standpoint of air changes per hour, we talked about that. ASHRAE Standard 170 requires 20 air changes per hour inside the space. That's a whole lot of air movement. We probably have 1 or 2 in this space. So equate that. That's a lot of air movement in that space, of which 4 air changes are 20% of the total airflow needs to be outdoor air. That's a lot of outdoor air to bring in. In a space like this, we might be getting 5 or 6 or 7% if we're lucky. 20%. That air's humid. That air's hot. That creates a problem, right? It really does. Then it tells us whether the room needs to be exhausted. It does not, because we have to maintain a positive pressure. If we exhausted the room, we couldn't maintain positive, so we don't necessarily totally exhaust hospital ORs. That makes sense too. It tells us, can the air be recirculated through a little fan coil type system? You know, and it cannot. It needs to come from a central station air handler, typically with high levels of filtration. We talked about that and how important it is, right, to the health and well-being of those in the space breathing the air. We want to get the particles out of the air. And then comes the part I love, design relative humidity. ASHRAE tells us we need to design the hospital operating room to be somewhere between 20 and 60% relative humidity. And from a temperature perspective, somewhere between 68 degrees Fahrenheit dry bulb and 75 degrees Fahrenheit dry bulb. So, hospital operating rooms, from a temperature and relative humidity perspective, should be designed to be able to achieve somewhere between 68 and 75 degrees Fahrenheit dry bulb and 20 to 60% relative humidity. How's that working for you? Yeah, how's that working for you? I'll ask again. Anybody? Are those great numbers? Is everybody happy? Are your ORs always compliant? Is it never raining in your OR? I didn't think so. Okay? ASHRAE goes on to tell us in another document that depending on the type of surgery or the classification of surgery that we're having, we may want different temperature levels. So for example, for heart, orthopedic, and neurological surgeries, we may want to maintain those spaces at lower temperatures. Cooler, colder, right? How cold? 55, yeah. Okay. Well, if I look at the standard, I'd say 68. That's the low end of the standard. Is that what I want to design to maintain happy, go-lucky surgeons? You know? It's not, and we're going to talk about why. But this is a problem, right? Now, there is a narrative note O to this standard that nobody ever reads, and I didn't bring it up, and I'm going to paraphrase. It basically says, if there's a reason to do better, you can do it. What better reason than surgeons that want to be productive? What better reason than infection control that doesn't want wet environments? What better reason than facilities managers that don't want to run around punching thermostats all day long? That's a pretty good reason in itself. But if we can keep those surgeons happy, there's nothing wrong with that, and we can do it. Okay? Let's keep going. So, hospital operating room environmental design is a three-legged stool. Certainly temperature is important. Again, dry bulb temperature, the temperature on the thermostat, it's a part of the standard, right? 68 to 75 or whatever. I don't even remember. Whatever it was. Doesn't matter. Doesn't work. As well, relative humidity, 20 to 60%. We know that's important. We've got two legs of the stool. The third leg is dew point temperature because it's so important. to assessing how well we're dehumidifying the air. And I'm going to prove that to you in the next few slides. But I ask you this, when you look at the standard, where's dew point temperature? I'll give you a little hint. It ain't there. It ain't there. We answered the question. Why? Why are we having problems? Because we've only got 2 legs of the 3-legged stool on the ground. And when you sit on the stool, it falls over. We are not and have not ever had a requirement to monitor or to assess or to design to dew point temperature in ORs or other spaces. Does anybody know why? Because that's just not the way we've ever done it before. It's just not the way we do it, right? We've just done it this way forever. And you know what? I haven't heard any complaints. Oh boy, let me tell you. It's just because that's not the way we've done it before, but it doesn't mean it's right, and I'm here to suggest to you that it's a huge problem, okay? And we need to overcome this, and I'm going to show you how. So, dehumidification is the process of removing excess moisture from the air or from surfaces, right? I want to dry things up. Neither temperature nor relative humidity alone or in combination is a measure of the absolute temperature. Again, I need to assess the absolute moisture in the air in pounds or grains or vapor pressure differential, or view it from a dew point perspective to be able to understand where I'm at and then determine where I need to go to get the air to where it needs to be dry. Okay? Without that, it isn't going to work. Relative humidity is relative to the air's temperature. In itself, it means nothing. Let me ask you right now, in a room at 75 degrees Fahrenheit and 50% relative humidity, or in a room at 80 degrees Fahrenheit and 40% relative humidity, which room has more moisture in the air? 75 degrees and 50% relative humidity, or 80 degrees Fahrenheit and 40% relative humidity. If I'm gauging it on relative humidity alone, I would assume the 80-degree room would have less moisture in it. It has more. It has more moisture, more absolute moisture in the air. You cannot assess the amount of moisture in the air based on temperature and relative humidity alone. You have to look at the absolute moisture in the air. Okay? Trust me on this. It gets us in trouble all the time. All right? So the train has come off the tracks. We need to get it back on because we're not assessing dew point temperature and other metrics properly. All right? So what is dew point temperature? Or more specifically, what is dew? Has anybody ever walked out of the front door on an early spring or summer day and stepped out into the grass in your bare feet and noticed that it's all wet? And you look around and it looks like it's rained in the yard. But you look on the sidewalk and the street and the house and the roof, it didn't rain last night. But the grass is wet, right? Does anybody know why that happens? Why do we form dew on the grass in the morning? Well, I'll tell you why. During the day, we have this thing up there called the sun, and it's radiating heat down towards the Earth's surfaces, and it's heating the surface of the air all day long, or the surface of the Earth all day long, right? And at night, the sun goes away, and the sky becomes a big, black, dark hole that's very cold. So at night, when the sun goes down, all that heat that has radiated to the Earth during the day begins to re-radiate back up towards space. It's something called radiant cooling effect. And it can chill the surface of the Earth and objects very deeply, make them very cold. And in fact, the surface of the grass is probably going to be colder than the air temperature that's above the grass, and most certainly it's going to be colder than the dew point temperature of the moisture in the air at the surface of the grass. So the surface has been made cold. When the surface is below the dew point temperature of the air that surrounds it, moisture condenses out of the air onto that cold surface, and we get moisture on the grass in the morning. Amazing, huh? Pretty cool. Dew point. Same thing happens on the hood of your car. If you leave your car outside overnight in the driveway instead of pulling it into the garage, the top of the car, the hood, the window, and the top has been exposed to that cold nighttime sky, which pulls the heat off of the car, chills the surface of the car to be below the dew point temperature of the air, that surrounds the car, and moisture condenses. But just on the top. Have you ever noticed the sides are dry? They're not exposed to the cold, deep, dark space environment above. There's no radiant cooling effect there. It's just those surfaces exposed above. So anytime you chill a surface below the dew point temperature of the air that surrounds it, that surface will condense moisture, and you will, in theory, dehumidify the air, right? That's how we do it. Does that make sense? Okay, so dew point temperature is very important in assessing where condensation will occur and where it won't. Think about cooling coils. I want condensation. I can determine what I have to do to make the air condense based on the coil's temperature. Think about a register or grill above a hospital operating suite. I do not want condensation. I can assess what the surface temperature of that grill needs to be based on the dew point temperature of the air and make sure that it's warmer and no condensation occurs. That is incredibly powerful. That's how we solve problems. But it's also how we design jobs from the start so we don't have problems. Wouldn't that be cool, huh? We can do it. Psychrometrics. So light bulbs begin coming on. Once we determine the air's dew point temperature, we can then determine how cold a surface needs to be to condense moisture from the air. Again, I mentioned cooling coils, good condensation. I want condensation. I want to dehumidify the air. And I've also mentioned non-porous building surfaces, which are bad. I do not want condensation. I can assess both. I can design buildings to achieve both of these at the same time done right. Okay? Now let's take a look at a house, just for fun, and let's plot dew point temperature on a psychrometric chart so you know how it's done, so that you can see this isn't hocus pocus, right? And psychrometrics has been around since the early 1900s, right? Willis Carrier, godfather of air conditioning, the father of air conditioning, invented psychrometrics and the psychrometric chart. This isn't not anything new. So in our home, for example, we may want to maintain it at 75 degrees Fahrenheit, dry bulb. Remember, that's the bottom level of run of numbers there. So 75 degrees Fahrenheit and maybe 50% relative humidity, which my little pointer isn't working very well, but it's right here. It's the relative humidity line that falls right in between 0 and 100. 50% relative humidity. And if I plot that point on the psychrometric chart and I draw a line horizontally from left to right, it will intersect the dew point temperature over here on the far right-hand side. You can see that this is my dew point temperature scale. It's 55 degrees Fahrenheit. It will also intersect the psychrometric chart at 100% relative humidity, which is 55 degrees Fahrenheit, 55 degrees wet bulb, 55 degree dew point temperature. And that's how I assess the dew point temperature in the air. I come in with a temperature meter and a hygrometer of some type. I measure temperature and relative humidity. I plot them on a psychrometric chart, and voila, I've got the dew point temperature. It's not hard to do. You just got to do it, right? Now, if you downloaded the app, you can do it there as well. You measure temperature and relative humidity. You come in and simply plug them in, 75 degrees Fahrenheit, 50% relative humidity. You get away from all this stuff over here. And right there it tells you 55.2 dew point temperature. It actually gives you the dew point temperature, decimal point to the right, so it's just a little bit more precise. Okay? This is so important to do. All right? Now, I'm going to tell you right now, and I'm going to say this a couple more times, it is important. We are assessing the dew point temperature in the air, in the environment, and where we want to maintain it. In order to achieve it, the HVACD system has to provide drier air to the space. The dew point temperature of the air coming out of the HVAC system needs to be lower to be able to absorb the moisture load in the space and maintain the space at that dew point temperature. All right? Look at it this way. If you're sitting in your living room in the summertime at home and you want to maintain your living room at 70 degrees Fahrenheit and it's a hot summer day outside and you turn on your air conditioner, do you blow 70 degree air out of the register to keep the space at 70 degrees? No, you can't. It's got to be a delta between the air provided and the space to absorb the air conditioning load, right? I might blow 55 degree air out of that register to maintain 70 degrees in the space. It's the same thing with moisture. The air's got to be drier than the space in order to absorb the moisture load. People forget that. Train comes off the tracks all the time. It's really important. I bring it up now because I'm going to talk about it a couple more times moving forward, okay? So this is going to be a little more fun. I've talked about dew on grass. I've talked about dew on the hood of a car. I'm going to talk about dew on a beer bottle. That's more fun, right? Who doesn't want to talk about that? Who has never taken a cold bottle of beer out of the refrigerator on a hot summer day, and even in your house you see condensation forming on the outside of that bottle, right? Happens all the time. It's a cooling coil, okay? And this is simply a metaphor, if you will, the beer bottle for a cooling coil. We're talking about a chilled surface and its ability to condense moisture. That's all I'm talking about, but beer's a little more fun, right? Let's say I've chilled that bottle to 46 degrees Fahrenheit coming out of the freezer. I pull it out of the refrigerator, all right? Now, if the air in the space has been measured at a dew point temperature higher than 46 degrees Fahrenheit, it might be 47, 48, 49, 50, who knows what it is, right? Since the surface temperature is below the dew point temperature of the air, we know that moisture will condense on the outside of that bottle, and I will dehumidify the air. Will I not? I will, right? Now, as well, if I come into that same space and I measure the dew point temperature below 46 degrees Fahrenheit, maybe it's 45, 44, 43, 42, no moisture will condense because the air is already dry, right? The surface temperature is above the dew point temperature of the air and no moisture will condense out of the air onto the bottle. It's pretty simple stuff, right? If I want to take my space from a 46 degree dew point down to a 45 degree or 44 or 43 degree dew point, I need to make the bottle colder. It's the only way to dehumidify the air. I need a colder bottle. I need a colder coil, right? It's really simple stuff if you look at it with the right perspective, right? Dehumidification strives to remove moisture from higher dew point temperature air. By lowering its dew point, the air's, we can maintain more compliant, comfortable, and productive environments. Lower dew point temperatures allow for cooler and drier operating rooms, achieving lower relative humidities and getting away from some of the issues that we've discussed previously with comfort, compliance, condensation, HAIs, SSIs, and all that stuff, right? Let's delve into it a little bit more. So, let's take a look at a house. Let's take a look at a hospital operating room. And my question to you is one like the other? Should we be designing the environments of hospital operating rooms to be the same as we design residential homes from a standpoint of temperature and relative humidity? What do you think? Anybody say yes? Doc? She says no. I'd agree, but you know what? It's not what we're doing. That's not what we're doing at all. Take a look at the design standards, 68 to 75. I suggest to you that depending on how efficient you are, how much of a greenie or sustainability freak you are, you may maintain your thermostat somewhere between 68 and 75 in your house. I know in the wintertime I set my thermostat for 68 degrees Fahrenheit, and I know in the summer I set it for 75. I do that. Those are my exact numbers. And the humidity in the space is going to vary somewhere in between 20 and 60%. If I'm up in Minneapolis in the wintertime, I'll be lucky to get 20 to 30% relative humidity. I usually get 40 to 45. It's perfect. I think of you every time I look at my little hygrometer, summer or winter. I'm usually always above 40%. I live in Austin, okay? Now, in the summertime, when I'm keeping my thermostat at 75, my indoor relative humidity may be somewhere between 45 and 55%. How about you? That's a house. Those are house standards. Why are we doing it like this? You know the answer. Because that's the way it's always been done. Is there any inkling of doubt in your mind why that doesn't work for people that are dressed like this over on the left-hand side, that are basically wrapped in cellophane doing jumping jacks? Do you think house standards are going to work for them? Why are we doing it like this? It's a recipe for disaster. It does not work. Okay? Let's keep going. So our home is 75 degrees Fahrenheit, 50% relative humidity. It's a 55 degree Fahrenheit dew point temperature. Our OR at the point of diminishing complaint should be designed to achieve 60 degrees Fahrenheit at 40% relative humidity. That's a 36-degree dew point temperature in the space. Is one like the other? Is 36 anywhere near 55? Well, yeah, kind of, sort of, I guess, if you extend the numbers out far enough. But I'm going to tell you, in the world of comfort and compliance, it's nowhere near, right? Now, remember, I said that the HVAC air provided to the space has to be drier. These are the space conditions I want to maintain. The dew points I provide to those spaces would be lower. Just a caveat. That'll become important in a minute or two. Just remember that, okay? Quick refresher. We have a 46-degree bottle that we've taken from the refrigerator, or I have a 46-degree chilled water coil surface, all right? We know that if the dew point temperature of the air is higher, it will condense moisture on the outside of that chilled surface and dehumidify the air. And if the dew point temperature is lower, it will not. And if I want to achieve a lower dew point temperature, I need a colder bottle of beer. Remember? Easy stuff. So, to my hospital facilities managers in the world, let's put some brass tacks to this now, right? What chilled water temperature are you running in your hospital? 40 what?
40, 41.
40, 41? Anybody else? Come on, I see you smiling. You got a number? It's okay. Oh, you're with him? Okay. 40, 41's kind of low for a hospital. The national average, based on what ASHE tells us, ASHE is the American Society for Healthcare Engineers, the average in the United States of America is 42 degrees Fahrenheit chilled water temperature leaving the central plant. That means it's probably a little warmer by the time it gets to the coil, okay? Why are we designing hospitals at 42 degree Fahrenheit leaving chilled water temperature? You know the answer. Because that's the way we've always done it. That's the only answer I can figure out, right? And why we put hospital operating rooms on the same loop with the rest of the hospital befuddles me. I don't know why, because it doesn't work. This is a problem, right? 42 degree chilled water will give you a bottle surface temperature or a chilled water coil surface temperature of about 46 degrees Fahrenheit, and it will achieve about a 49 degree Fahrenheit leaving air dew point temperature. Remember what I told you? That's what's important. That's what will maintain the space, okay? So, 42 degree chilled water, 46 degree surface temperature, 49 degree dew point temperature. The reason 42 degree chilled water doesn't create 42 degree leaving dew point is thermodynamics and the inefficiencies in heat transfer, right? I start out cold and I end up warm. There's inefficiencies in every leg of this loop as I try to keep the temperatures as low as I can, but suffer with the inefficiencies of thermodynamics and heat exchange design, okay? This is the real deal. And I'm going to tell you right now, if you're a hospital and you're using 42 degree chilled water and you're getting a 49 degree leaving dew point, you're doing really, really good, because that's a tight approach, okay? I won't bore you with that, but they know what I'm talking about. While these HVAC conditions may work well for less humidity sensitive areas, maybe even other areas in the hospital like patient care, right? They rarely work well for ORs, sterile processing, and other critical care areas where staff are heavily garbed and working hard, wrapped in cellophane and doing jumping jacks. It ain't going to work. It's not going to achieve a low enough relative humidity to impact that evaporative cooling effect and draw that moisture from their skin through multiple layers of clothing. It needs to be drier, okay? Also, avoiding condensation on surfaces is another important consideration, and at these dew point temperatures, any excursion in humidity in the space is what's causing those issues. I saw somebody going, yeah, with raining in the ORs at certain times of the year. We look at our 46 degree coil surface temperature, and most certainly the dew point temperature of the air in the home is higher. It's at 55. I will condense moisture. The dew point temperature in the OR is at 36. By design, if we do it right, it is too low to condense moisture. That coil will do no good. I can take care of the home. I can take care of the standards that ASHRAE's put forth, but I cannot drive it to where it really needs to be to impact surgeons, keep them comfortable and productive. That's the problem. Here's what happens in the real world. This is one hospital operating room, okay? 3 different scenarios. So let's focus on the one on the left for now, right? With the temperatures that I just mentioned through a typical central plant, I'm going to end up achieving a 52-degree dew point in the space. Trust me. I did the math, okay? And at 70 degrees Fahrenheit, that OR could be maintained at about 53% relative humidity. Now, that relative humidity isn't terrible. That's what I might like in my house, you know. For me, up here, walking around in a suit jacket, 53% probably isn't too bad. But I'm going to tell you right now, 70 degrees is sure too warm for an orthosurgeon, right? I mean, just the temperature alone, way too warm. They need it colder. So, as a good facilities manager, when the complaint comes, make it colder in Doc's OR, what do? You go and to your BAS system and you drop the temperature in the OR to 65 degrees Fahrenheit. Do you know what happens to the relative humidity in the space when you do that? Because I have not dehumidified the air any further. I still have the same 42-degree chill water being pumped out, dehumidifying to a certain point. What happens when I lower the temperature and I don't dehumidify the air any further? Relative humidity goes up, and it's going to go up within a point or two of this exact number in a hospital ortho operating room. It's going to be about 63% relative humidity. Now that's in red for a couple of reasons. Number one, the space is now cool and clammy, right? Less evaporation of perspiration from their skin into the air because the air is more humid. And I'm also out of compliance with ASHRAE Standard 170. How many of you run issues with regards to humidities above 60% in your hospital operating rooms in the summertime? And will admit it. If you don't want to admit it, it's okay. In theory, you're not supposed to be in there. And many hospitals won't. They'll offload surgeries. Many others will just go, oh, gosh, let's just get it done. Let's get through this, right? You're out of compliance, and it's not comfortable. Now, Doc still isn't comfortable. Doc's probably worse off than he or she was when we started at the higher temperature and the lower relative humidity. So the complaints are still coming. Doc wants it colder. So what do you do as a good facilities manager? You make it colder. You lower the temperature to 60 degrees Fahrenheit, and in fact, you make it so cold in that OR that you could hang meat, right? It's a meat locker, and Doc still isn't happy. What happens to the relative humidity? Kaboom. It's going to go up to about 75%, plus or minus 1%, one way or the other. These are real world numbers, right? And now it is cold and clammy for the doc. He's standing in a cold environment underneath 3 sheets of material, and he or she is wet. And that condensation is beginning to get cold too. But they're still overheating. No evaporative cooling, right? And I'm way out of compliance with ASHRAE Standard 170. And just an inkling of humidity excursion. Let's say it rains outside and excess humid air gets into the system and my system isn't designed to handle it. And I'm chugging along at this and all of a sudden the humidity goes 75, 76, 80, 85. What happens from above? We're sent this little message. You're messing with Mother Nature. We condense moisture. We form dew on those cold surfaces and it rains in the OR, right? So, why the problem? It's real simple. We're not making our beer bottle coil cold enough. We can't do it with 42-degree chill water. And we're not designing systems based on standards that need anything lower than 42-degree chill water, so why provide it? Or why provide something that's even better than chilled water at doing the job? Why not? Because that's not the way we've ever done it before. That's not the way we do it, right? We haven't done it that way. We got to start thinking differently. We really do if we want to solve these problems. 60 degrees Fahrenheit, 40% relative humidity is a 36-degree dew point temperature in the space. I mentioned that, and I tell you that simply because we know that the air has to be provided to the space even drier. It needs to be provided to the space at a 32-degree dew point in order to remove the moisture load and achieve a 36-degree dew point temperature in the space. The problem with 32-degree dew point temperature air is that moisture freezes at 32 degrees Fahrenheit. It won't work. Even if we did design a cold enough system, We can't achieve that dew point temperature because the condensate on the coil would freeze into a block of ice, and air doesn't move through a block of ice very well, does it? So, are we just stuck? Is there nothing we can do to achieve the point of diminishing complaint? And I'm going to tell you, I wouldn't have written about it if there wasn't a way to achieve it, and I'm going to tell you how we do it right now. This is what happens when coil surface temperatures approach, are at, or are below 32 degrees Fahrenheit. Our beer bottle turns into a block of ice, and our cooling coil turns into a block of ice, and the train comes off the tracks, okay? What we need to look at is something that does it a little differently, something that dehumidifies the air without having to use a cold surface to condense moisture. And that is a desiccant, in particular a solid desiccant. And a great solid desiccant is silica gel, and you're all familiar with silica gel. Whenever you order something off Amazon, for example, and they're going to put it in a box and they're going to ship it to you from point A to point B, and it might be humid outside, right? And that product in the box is hygroscopic. It's moisture-seeking, moisture-loving, right? And moisture might damage it during shipping. Maybe it's, I don't know, leather goods, maybe it's electronics, maybe it's food. Got to keep it dry. You know, the FedEx truck isn't typically air-conditioned in the back end. It's just open. You got the door open all the time, right? So what I do is I drop a little packet of silica gel in the box, and the silica gel is at a very low vapor pressure. It's little beads, and they're very porous, and they're at a very low vapor pressure. Remember I talked about vapor pressure in assessing dehumidification? Moisture moves from high vapor pressure to low vapor pressure. The moisture in the warm air in the summertime is at a very high vapor pressure, and the silica gel is at a very low vapor pressure when it's stuck in the box. And as long as you seal the box up quickly, that little packet will adsorb moisture. It will suck the moisture out of the air as a molecule, and it will hold it in the pores of the silica gel as a molecule, never condensing, never getting wet. And when you get your box and you open it up, it's miraculously dry. I mean, we never notice it. We just notice the packet, and we do what we're told. We throw it away. And the reason we throw it away is because it's reached equilibrium. It's done all it can to absorb moisture from the air. It's now full of moisture molecularly. Again, it's not wet, but it's holding water molecules molecularly in the pores, right? And I have to be able to dry it out. I want you to think of a sponge that's holding water, but not liquid water. I can't wring the sponge out because it's not liquid water. But what I could do is heat the sponge up and increase the vapor pressure of the moisture to be above the vapor pressure of drier air in the environment, and it would then desorb that moisture, it would spit it off into the air, dry the sponge out, and I could use it again. And if I took that little packet that's full of molecular moisture and I put it on a cookie sheet and I stuck it inside my oven and I hit it with about 100, 110 degrees Fahrenheit, I'd do exactly that. I'd increase its vapor pressure, I'd blow the moisture off, I'd dry the desiccant out, I could then immediately put it in another box. It's dry, it's at a low vapor pressure, it's going to adsorb moisture, and I could ship it to my friend, and whatever I sent that friend, they'd receive a dry product on the other end. And we do exactly the same thing with desiccant dehumidification, where we need to hit low dew point temperatures, particularly those that are at, let's say, approaching at or below 32 degrees Fahrenheit, where moisture would freeze if condensed on a cold surface. Anybody drive an electric vehicle? Oh, I forgot we're in Oklahoma. I get the same response at, oh, come on. Nobody's going to admit it. I know somebody in here is driving an electric vehicle. I will assure you this, you're using something that has a lithium battery in it, right? So lithium, which goes into the batteries which are in electric vehicles, is a very corrosive rare earth metal, right? It will corrode and combust at ambient relative humidities above about 4%. Think of that, 4% relative humidity, and a lithium battery will go boom. Have you ever seen these lithium battery manufacturing fires that you see on the TV all the time anymore? I'm not going to suggest that it's because the lithium has come in contact with moisture in the air in the plant, but I will assure you that if it does, this will be the result. And in applications like that, we use solid desiccant dehumidification to achieve dew point temperatures at -80 degrees Fahrenheit. That's the equivalent of the amount of moisture in negative 80-degree Fahrenheit air if you could cool it traditionally, which you cannot because moisture would have been frozen on that coil way up the temperature scale range, right? But at a negative 80-degree supply air dew point, I can maintain a lithium battery manufacturing plant at about 1% relative humidity. Amazing. And if I can do this here, man, I can do it easy in hospitals. That's light lifting for solid desiccant dehumidification, okay? I wrote an article about it in November of 2023, specifically catering to hospitals and operating room environments, talking about a wealth of benefits using desiccants. If you'd like it, my EEI team can certainly share it with you. I'm cramming it down their throats all the time. You may already have it. I know Cody back there, I think he has 100 of them in his briefcase at all times. Thank you. This is what they look like. Gosh, that's a solid desiccant dehumidification unit, right? It's no big deal. It looks like other units that you probably have throughout your facility and on your roof. It shouldn't scare anybody. This is not that big a deal, right? This is what they look like on the inside. That shouldn't scare anybody. Very durable, very robust, very well built. You will notice the picture on the right is the solid desiccant wheel. That is a wheel that has a substrate material that is fluted. Air can pass through it. It has been impregnated with silica gel, not the beads. It's a little bit different blend, but it's silica gel. And as the air to be dehumidified passes through the wheel from one side to the other and comes in contact with that silica gel that's at a very low vapor pressure, the silica gel adsorbs or sucks the moisture out of the air and holds it as a molecule, never condensing, never getting wet. And as the wheel loads, I rotate it into an opposing airstream, hit it with a little heat, dry it out. It circulates back around and it's ready to go. And as long as the wheel is turning and the fans are moving air and the heater's firing, you've got dehumidification. It's thermodynamically eloquent. Very few moving parts, very easy to maintain, very easy to service, and a very reasonable longevity from a standpoint of life cycle time, right? And incredible energy efficiency and sustainability benefits if done right, I assure you that. So, anytime you have surfaces that are air conditioning and attempting to dehumidify the air at surface temperatures approaching at or below 32 degrees Fahrenheit, you cannot use a traditional refrigerant-based system, whether it be chilled water or DX, because you'll freeze the coil. That's it. You're done. In cases like that, you have to use an adsorptive technology such as silica gel. It's the only way to get it done. All right? And that is how we make sure that we keep these folks on the left satisfied, right? Keep them happy. Facilities management, wouldn't you love to get that complaint off your list of to-dos? I want it colder, I want it colder, I want it colder. And it's never cold enough because it's not dry enough and it can't work. And for my team over here on the right, infection control and facilities, you're smiling because you've got more time to do other things. You're not chasing thermostats. You're not worrying about a bucket and a mop going around and squeegeeing up condensate issues that might occur in an OR when it rains or other areas of the hospital where you have condensation and the potential for microbial contamination. Maybe you can actually get together and have a cup of coffee and enjoy yourselves on a shift. Wouldn't that be nice, huh? That's it. That's all I got. I suggest to you that it's time for change. That's all I suggest. And if this has turned a light bulb on and you're going, yeah, we have these problems. We've always had these problems. And we've been told they can't be solved. I'm here to tell you that's not true. They can be solved. Reach out to EEI, and they and I will be happy to come in and have a more extensive conversation. And with that, I'll open it for Q&A if there is any. Yes, here you go.
Thanks, Dave. I'm glad we have that 40%.
Yes.
In common. I'm wondering, why can't desiccant technology be used to also release water vapor into the air in dry conditions? It seems like, well, I know that's how tick saliva works. Like when ticks are really dry, they absorb moisture.
Yep.
And when ticks bite your dog and fill it with blood, they are able to release excess water.
Interesting.
Yeah, so Mother Nature's got to figure out how to
Yeah.
do both.
Yeah. Well, so to your point, it can release moisture that it has adsorbed. So I can adsorb moisture to a certain point when I reach an equilibrium based on vapor pressure, right? And at that point, I've absorbed all the moisture that I can, so my sponge is full of molecular moisture. It can't take on anymore. At that point, if I heat the desiccant up, I can desorb that moisture, and I can use it over and over and over again to adsorb based on high vapor pressure in the air, in the moisture in the air, to the lower vapor pressure of the pores of the silica gel, adsorb moisture and remove it, heat it up, increase that vapor pressure, blow the moisture off, and use the desiccant again as a dried material. Now, how it could be used in medical applications, my guess is it probably is. You know, it says don't eat on the packet. You could, so if you want to do an experiment, you know, but it probably won't stay around long enough for the experiment to be seen through to fruition, if you know what I mean. I know you do. Yes, here, I'll give you this.
So could you reintroduce that moisture back into the area through that unit? Because we have the desiccant wheel and we have too low of humidification.
In certain areas? Or in the area you're, well, then you need to adjust the desiccant unit, not to,
That's what I was wondering.
yeah, it's just tweaking.
Okay.
Tweaking, you know? I talk about tweaking all the time, you know? This desiccant material can be manipulated and controlled to maintain anywhere from a negative 80 dew point to 32 degrees Fahrenheit positive, right? Or even higher if you want it to. It's just getting in and altering the controls to make sure it does that. So if you're over drying, let's just have a conversation.
Okay.
It can be fixed.
Thank you.
Yep. Anybody else? Here we go. Hold on. This way I don't have to repeat the questions. It's just a lot easier, and I need the exercise.
Oh, I was just going to clarify the two questions that were asked. I mean, there are technologies where people will just use an enthalpy wheel to exchange return air or air that they're exhausting out of the building to basically cool cold, dry air in the winter, and then that adds moisture and sensible heat back into the airstream so that you can reduce heating load and humidification load. So those products do exist, and they are used in certain applications, usually for like energy recovery for ventilation.
Yeah.
Just
Oh, that's Brian. Yeah, Brian made a really good point. Everybody looks at the wheel and they go, a wheel's a wheel's a wheel, right? It's not. A desiccant dehumidification wheel is not an energy recovery wheel, and an energy recovery wheel is not a dehumidifier, period. And if you're thinking they are, assuming they are, confusing one with the other, that may be the problem, right? Well, maybe we need to talk about that. Because an ERV will not dehumidify the air. You need a dehumidifier to do it. It will exchange energy. That's it, right? Anybody else?
How do you clean the desiccant wheel without damaging the silica if it gets clogged up?
So the desiccant wheel is always dry, right? It's holding the water molecularly, never condensing, never getting wet. If something gets into the flutes, and these are pretty big flutes, you can see through them from one side to the other. If something gets into the flute and clogs it, you can blow it out with compressed air from one side to the other, right? You can take the wheel out and wash it with soap and water. Or because it's rotating between two opposing airstreams, and I didn't really talk about that, we have the process air moving in one direction and the regeneration air moving in the other. Anything that might plate out on one side will typically be blown off when it rotates into the other airstream, and it rotates at 8 revolutions an hour, so it's always self-cleaning. But because it's dry and never gets wet, it's not like a cooling coil that'll fill up with junk that gets in and gets wet and plates out and grows mold and mildew and fungi. That's not a problem or a consideration with the desiccant wheel. That's part of its value proposition to infection control. They love that. Get away from those wet, moldy, stinky cooling coils, right? Big deal. Anybody else? Here we go.
What's the life expectancy?
Life expectancy, how well do you maintain your filters? You tell me. Keep your filters clean goes a long way. That not just with desiccants, but with any HVAC system, right? I would say on average, you're going to see a desiccant dehumidification wheel last about 10 to 12 years, maybe a little less, maybe a little bit more. I've got some out that have been churning and burning for 20 years plus. If I get something in the wheel that shouldn't be there, like an oil mist or something, it will coat the surfaces of the wheel and it will become inefficient in transferring moisture, and everybody goes, well, the wheel. The wheel's bad, we got to replace it. You just got to clean it. I can't tell you how many wheels are replaced because they're losing capacity because they haven't been maintained properly. They're getting dirty, right? Blow it out with some compressed air and see what happens before you buy a new wheel. The desiccant itself, somewhat limitless, right? Unless you get something caustic in there that has a tendency to deteriorate what we adhere it to the wheel with, it should last for theoretically forever. Keep the wheel clean.
But won't it ever get full of molecular moisture at some point?
Well, if you don't regenerate it, it will. It'll reach equilibrium, right? That's why we take it from adsorbing moisture and rotate it over to a heater in an opposing airstream that increases the temperature and blows the moisture off and dries the wheel out. So it's self-refilling, self-regenerating, if you will, just like the packet would be if you took it out and stuck it in your oven and then stuck it in another box. You dry the packet out, stick it in a box, low vapor pressure, send it to Grandma, and when Grandma gets her fruitcake, you know, who cares if a fruitcake gets there, one piece or not, but it'll you know what I'm getting at, right? Questions? Another?
I got another one. What's the biggest technology change you've seen hit the desiccant wheel space? Has it been the same for the last 20 years?
Yeah, the biggest change that I've seen hit the solid desiccant dehumidification market has not occurred in the 43 years I've been in the industry. Other than more efficient fans and more efficient componentry and better controls and more precise environmental capabilities and stuff like that. This technology has been around 100 years. It ain't nothing new. What do I expect to happen in the next 100 years with solid desiccant? It's not much. There's other technologies coming out, membrane technology and stuff like that that's really cool. May replace solid desiccants, but probably not in my career, probably not in yours. Why don't we see it more in healthcare applications? Anybody got a solid desiccant? You do, right? You've got one. Are you happy with it other than it's just doing too much? How often do you say that?
I'm an alarmer, so I've been dealing with the humidity issues.
Too low.
First time
Now get with EEI and let's get on a conversation and talk about it. I don't know whose you've got. I don't want to ask. I doubt it's mine. It's not. But I can help you diagnose it. All right? That's a shame. That's just communication, right? Lack of understanding on everybody's part to give you what you need. Okay? Question in the back? No. Just stretching? That's fine. I understand. It's getting late. Anybody else before I close? Another question?
On your wheels, I know your equipment's only going to last so long. On your desiccant wheels and parts, things like that, how long do you usually keep your desiccant wheel parts before they go obsolescence?
Wow, good question. So in other words, if I buy one today, in 20 years, am I going to have trouble getting a wheel?
Right.
No.
Okay.
No. The wheel is a certain size, diameter, right? There's 3 or 4 major manufacturers of wheels. They're all manufactured fairly consistently from one to the other. There's, pros and cons to one versus the other, but I might have a 36 diameter wheel that's 12 inches deep that's impregnated with 80 pounds of silica gel. Right off, I won't say off the shelf, but it's something that's common and consistent throughout the industry. And based on the size of the wheel and the diameter and the amount of desiccant in it, they just build them. You could probably do it in your garage if you wanted to, believe it or not. I wouldn't suggest it, but anybody else? All right, with that, I will say thank you and good afternoon.